everyone, and welcome to the sixth module of the Docker course. This module is about Docker storage and volumes. It directly corresponds to Domain 6 of the Docker Certified Associate exam and accounts for 10% of the exam weightage. In this module, we will first learn about the storage in general that is provided by Docker for running applications. We will understand the use of storage drivers and how to change the configured storage drivers on the Docker daemon. We will look into the Docker capabilities to provide persistent storage to the containers running on a Docker host. And lastly, we will learn about the various ways to manage data in running application. Provide the storage for Docker image run. It is used for reading the file system layers from the running container. Second is volumes, and these are the persistent data container storage. It is used by containers for using, capturing, or saving data beyond the life cycle of the container. The data is stored outside of the container boundaries and can be used by other containers or services as well. Last is the static image storage. Registry is used for storing the responsive repositories, which in turn store images. The images are stored for cataloging and are not in the running state. We will cover Docker Trusted Registry in the next module. As we learned earlier, Docker Hub is the default registry for Docker host. Docker image is built up from a series of layers. The layers are stacked on top of each other. When you create a new container, you add a new writable layer on top of your underlying layers. This writable layer is often also called as the container layer. A storage driver handles the details about the way these layers interact with each other. Because each container has its own writable container layer and all the changes are stored in this container, multiple containers can share access to the same underlying image and yet have their own data state. Docker uses various storage drivers to manage the contents of the image layer and the writable container layer. Each storage driver handles the implementation differently, but all the drivers are stackable image layers and the copy on write strategy. Copy on write is a strategy of sharing and copying files. In the perspective of Docker layers, it is done to achieve high efficiency. If a file or a directory exists in a lower layer within the image and any other layer, including the writable layer, needs read access to it, it just uses the existing file. But in case the another layer needs to modify the file when building the image or running the container, the file is copied into that layer and modified. So copy of the higher layer is only needed when there is a write operation done. In case of read, there is no copy of file done. This minimizes the I/O and the size of each of the subsequent layers. Now, a container occupies corresponding disk space on the Docker host. To view the approximate size of the running container, you can use the docker ps command. So let's get back to our Docker host and let's see how we can do this. So on our Docker host, let's check the running containers. We have a couple of containers running here. One is Redis and another is the Apache. We will run the command docker ps -s here. The output isn't clear, so I will format it first. A table using, okay, so we'll use a table and using the names. Okay, I want the image and of course the size of the container, the size. Okay, hit enter. Here are two different columns related to size. One is just size and the other is virtual size. So just a size is the amount of data on disk that is used for the writable layer of each container. For this container, it's a 0 byte. That is no data in the writable layer. And on Apache image, as you can see, the size is around 971 bytes. Now, whereas the virtual size is the amount of data used for the read-only image data, used by the container plus the container's writable layer size. Multiple containers may share some or all read-only image data. Two containers started from the same image share 100% of the read-only data, while two containers with different images which have different layers in common share those common layers. Therefore, you can just total the virtual sizes to get the total size. Okay. The total disk space used by all the running containers on disks is a combination of each container size and the virtual size values. If multiple containers started from the same exact image, the total size on disk for these containers would be the sum of writable layers of all the containers plus 1 time the image size. Okay, so we can check the Docker disk usage using the command docker system df. Okay, so let's get back here. Now here, if we say docker system df, so you have these under the sections, the containers, the local, right, and the build cache. Now there are 7 images on the Docker host, 2 of which are in active state, and this size is consumed by the images. Now for containers, there are 2 containers, both of which are in active state. Okay, and this is the size of the writable layer of the containers. We can get detailed information by running the command in verbose mode. So let's go back here and docker system df-v. This gives information about each entity. So far containers, it gives information about each one of them. So similarly for the images, it gives information about each image. As you can see here. Hello everyone. In this nugget, we will look at the storage drivers. Docker supports several different storage drivers using a pluggable architecture. Let's go to our Docker host now and check the storage drivers currently configured. So I didn't make any changes, so the current storage driver is default on CentOS. We'll just run docker info and then grep it to storage driver. The current storage driver, as you can see, is overlay 2. Now Docker supports multiple storage drivers per operating system type, but it has a prioritized list of which storage driver to use. Docker allows you to change the configured storage driver in the daemon as well. Docker supports the storage drivers. As you can see on the screen, these are the list of it. Very first is your overlay 2. This is the preferred storage driver for all the currently supported Linux distributions and requires no extra configurations. Second is your AUFS, and it was the preferred storage driver for older versions of Docker. So till 1806 it was being used. Let's also check the Docker version installed on our host. Okay, so let's get back here. Docker-version. As you can see, it is 18.09, which is higher than the 18.06, which is why it's using overlay 2. Now the next is the device manager. Device manager, it is used to be the recommended storage driver for CentOS and RHEL, as their kernel version did not support overlay 2. However, current versions of CentOS and RHEL now have support for overlay 2, which is now the recommended driver. The device manager storage driver is deprecated in favor of overlay 2 and will be removed in the future releases. Next is your BTRFS and ZFS. These file systems allow for advanced options such as creating snapshot, but require more maintenance and setup. And finally, the VFS is intended for testing purposes and it is not generally recommended for production use. AUFS and overlay 2 operate at the file level rather than the block level, whereas the device mapper, BTRFS and ZFS are block level storage drivers. Now, as part of this exercise, we will change the storage driver on our Docker host from the default overlay to device mapper. So let's go to our Docker host. The parent directory for images and containers is your var lib docker. Okay, so as you can see, I don't have permission here, so let's switch to your super user. So sudo su, and now let's cd to the Docker folder, var lib docker. Now this is a parent directory, contains the directories for containers, images, network, storage driver, and all the other stuff, and also the volumes, as you can see here. By changing the storage driver, all current Docker resources, which include containers, images, and volumes, will be unavailable for accessing by the new storage driver. You should commit and export any containers or volumes you want to keep and import them after the change. Otherwise, you will have a fresh blank Docker installation after the change of storage driver. Now, let's have a look at the steps to change the storage driver. Firstly, we need to export the data and save it. Then we will stop the Docker. Then we'll go ahead and edit or create, if it is not already existing, the daemon.json in the etc Docker folder. Then we will start the, okay, so that is in the folder. We will start the Docker, check whether the updated storage driver has been taken up or not. Once that is done, we will import the exported data. Now let's go back to our Docker host and let's see all of these steps. First, we will stop the Docker system by using service systemctl stop Docker. Now let's go to the etc Docker folder. And as you can see, there is no daemon.json here. So we will need to create the new one. So vi daemon.json. So have to make the new entry here, which is about the storage driver. So let's go ahead and make that entry here. Okay, should be the device mapper. So we'll be making the entry for the device mapper. Okay. So once that change is made, now let's save the file. Now let's go back and start the Docker. So systemctl start Docker. Now let's check the status of this Docker. So systemctl status Docker. You can see that the service is in the active state. If the daemon.json file contains badly formed JSON, then the Docker service does not start. Let's check it with Docker info now. So let's clear it a bit and then you can check it, Docker info, and we will grape it to the storage driver. As you can see that the storage driver has been changed and we get the warning that the device mapper storage is deprecated, right, and will be removed in the future releases. Okay, so now let's run the command docker image ls. We see that all our previous images are gone. We don't have anything. Similarly, if you do a docker ps-a, even our containers are lost, which is expected as we have changed the storage drivers. Now there is another way of configuring these storage drivers, and that is through the dockerd storage driver command. So let's go back. So first stop the Docker service. So systemctl stop Docker. Let's also remove the daemon.json file that I have. So we'll go to the Docker folder first and remove this file. Okay, first let's see the help for storage driver command. So let's have the different options which are available here. Dockerd help. Here you see that we can specify this storage driver to use docker d storage driver, and let's put AUFS. Right now, here it gives an error saying that the driver is not supported. Right, it is not supported. So let's run this one with the device mapper as an option. Docker D, and instead of AUFS we will use device mapper. As you can see, the Docker service is started. If now you want to stop this, I will have to do the Control C. So this is how the storage drivers work in Docker, and this is how they can be changed from one type to the other type. In the last nugget, we learned that the storage drivers are allowed to store the data in writable layer of the container. But there are certain disadvantages of doing so. The first is the data doesn't persist when that container is no longer running. If the container is removed, the data also gets removed. Second, a container's writable layer is tightly coupled to the host machine where the container is running. You can't easily move the data somewhere else. Third, writing into a container's writable layer requires a storage driver to manage the file system, which causes some reduction in performance, especially in high write intensive operations. Volume storage provides ways for an application or use to store data generated by a running container. It extends beyond the life or boundaries of an existing or running container. This storage use case is commonly referred to as persistent storage. Persistent storage is extremely important use case, especially for things like databases, images, file, and folder sharing. The big data collection activities also can be supported. Volumes have other benefits, such as allowing you to share the data among containers and persisting even when no running container is using them. You can manage volumes using Docker CLI command or the Docker API. This makes usage very helpful with the orchestration engines. Volume does not increase the size of the container using it. Volumes provide the best and most predictable performance for write-heavy workloads. This is because they bypass the storage driver and do not incur any of the potential overheads introduced by the provisioning and copy on write. In addition to mounting a host directory in your container, some Docker volume plugins allow you to provision and mount shared storage such as ICSCI storage arrays, network file systems, fiber channel. Volume drivers let you store volumes on remote host or cloud providers to encrypt the contents of your volumes or to add other functionality. No matter where the data comes from, this information is translated by the volume drivers plugin from the backend into the file system that can be accessed by normal tools meant to interact with the file system. Now, as shown in this diagram, each container can have one or more volume drivers using which persistent data is provided on local or remote systems. Hello everyone. In this nugget, we will see ways to mount data into a container. There are 3 different ways to do so, as you can see on the screen. First is volumes. They are stored in a part of the host file system which is managed by Docker. As seen earlier, they reside in a directory /var/lib/docker/volumes on the Linux platform. Non-Docker processes should not modify this part of the file system. Volumes support the use of volume drivers, which allow you to store your data on remote hosts or on cloud providers. Volumes are the best way to persist data in Docker. We will see why that is so shortly. Second is your bind mounts. Data may be stored anywhere on the host system. They may even be important system files or directories. Non-Docker processes on the Docker host or the Docker container can modify them at any time. And lastly, the TMPFS mounts. Container data is stored in the host system's memory only and are never returned to the host system's file system. If you look at the diagram, there is a container running on the Docker host. Volume providers provide storage to the Docker managed area of the host. Now, data through the bind mount can be stored anywhere on the host file system. TMPFS mount stores data on host system's memory only. Hello everyone. In this nugget, we will study volumes. They are the preferred way to persist data in Docker containers and services. Volumes are created and managed by Docker and are isolated from the core functionality of the host machine. When you mount the volume into a container, this directory is what is mounted into the container. A given volume can be mounted into multiple containers simultaneously. When no running container is using a volume, the volume is still available to the Docker and is not removed automatically. Now, volume can both be mounted into containers using the -v or --volume flag, but the syntax for each is slightly different. In the recent versions of Docker, it is recommended to use the --mount flag as the syntax is much clearer. Let's do some exercises to get the better understanding. First, we will try to attach it with the container using the volume flag. So on our Docker host, you can create a volume explicitly using the docker volume create command. We will name it as a test volume. Okay. So let's do docker volume ls. Okay. To check the volume, it is created successfully. Now let's run a container with this volume attached to it. So for that, we can use docker run itd --volume. We will use the test volume that we've just created. Then, and the colon. Then the volume path, that is /app and the latest image of Nginx. Now let's check the Docker with the ps command. Okay, so the container is up. Let's do an exec to this container. So docker exec it, the container ID that we want to use, and we will use the bash. Now we are inside the container. Now let's cd to the app folder and do ls within this directory. So let's try to find out what is there in this directory. Right now this is blank. We will create a file, a test file out here. And then give it some name, say test file or something like that. Okay, the file is created. Let's do ls out here, and there we have the file that we just created. Let's exit from this container now. Let us inspect the above created volume. So docker volume inspect and the name of the volume. The mount point on the local file system is mentioned here. Let's go to this directory now. If you do ls over here, there is only one directory. Okay, let's go to this directory, and then if you try to do ls here, there's only one directory data. This is the file which we created. Now let me create another file from here. So in this this is the file we have created. So let's do that. So this is what we have, both the files. Now let's go back and do the container. And let's go to this folder and ls. So we can see both our files that we have created are visible here. So now let's exit this. Basically, it's a mount that has been created from inside the container. Any change made either inside the container or from the Docker host is available to the other end. Okay, so let me do a docker volume ls now. I will try to remove the volume using docker volume rm command. Okay, we get the error message that the volume is in use. So let's do the docker ps here. Let's stop this container that we are seeing here. So docker stop and the container ID. Now let's do the docker ps-a. The container is in stopped state, as you can see. Let's see, clear this a bit. Docker volume ls. Now let's again try to remove this volume using the docker volume rm command. Docker volume rm and this particular volume name. Still, we get the error message. That means even if the container is in a stop state, the volume is still in use. So we will have to remove the container itself. So let's check it now. So docker ps-a. Okay. Now we will, okay, so let's remove this one. So now this container also is removed. Now we will try to remove the volume again, this particular volume. And this time the volume gets deleted, right? As we see, there is no volume left now. So the next exercise is to launch a container with volume attached, which doesn't pre-exist. Okay, so the expectation here is that it gets created at the runtime when we try to attach it. So let's run a container docker run itd rm volume test volume 2 colon the path app test and nginx. So container started successfully. If you do docker volume ls here, okay, let's ps. If you do docker volume ls here, the volume is successfully created. You can see that. Next is to launch the container with two volumes attached using the mount option instead of the volume option. Okay, so now let's go back. Let's run the docker. Let's clear this a bit. Docker run itd rm -- mount source is equal to test underscore volume 3 and the target we will give it as the path, that is /app, and then we will add one more mount source, that is test volume 4. Okay, and the target is again the another folder, that is app2, and we'll be running it with the nginx image. Okay, so now let's do the docker and ps. So here we can see shows the another container. Now docker volume ls will show you the other volume also created. So we see all volumes that we have created. If I go inside the container, we will do this exec in this container, and we will specify the shell docker exec it and the bash shell. Now, if we see here, we see the various folders that we have created here, app and app2. So let's exit from there. The next exercise is about removing the volumes. Docker volume rm we have already seen. Let's now see docker volume prune, which is used to removing the unused volumes from the Docker host. So let's go back to our host. Let's list the containers here. So let's stop both these containers now. Okay. And now let's verify with the docker ps-a. Both have been removed as well, not only stopped. At this point, if I list the volumes on my host, I see 3 volumes, which are not used by any containers in running or stopped state. If I do a docker volume prune, it would ask me for yes, I want to. It will remove all the volumes, and the reclaimed space is 0, as these volumes were empty. We didn't have anything. If I list the volumes again now, I will see none are existing because all are deleted. So this way we can play around with Docker volumes, create them, delete them, etc. In this nugget, we will learn about bind mounts. When you use a bind mount, a file or a directory on the host machine is mounted into a container. The file or a directory is referenced by its full path on the host machine. The file or a directory does not need to exist on the Docker host already. It is created on demand if it does not exist yet. We can't use the Docker CLI command to directly manage bind mounts. In case of volumes, we have commands like docker ls, rm prune, etc. So there are no similar commands for bind mounts. Some of the use cases of the bind mounts are sharing configuration files from the host machine to containers and sharing source code or build artifacts between the development environments on the Docker host and a container. So if you want to provide the configuration files or other artifacts through the bind mounts, then the directory structure of the Docker host needs to be consistent because the same container will be running on the multiple host. Just like volumes, bind mounts can be mounted into containers using the -v or -- volume flag, but the syntax for each is slightly different. If the volume flag is used to bind a mount directory that doesn't exist, then it gets created automatically. But with mount flag, the Docker doesn't create the file or directory automatically. It errors out. Here, we will do a couple of exercises to understand this concept better. First, we will launch a container with bind mount using the -- volume flag. So let's get back to. So I have this folder called home/mount/volume1. So let's get into this folder. And if I list the files in this folder, they have a file called test1.txt. So it has some content. So we will use this file to mount onto this container. Okay, so let's try to run this command, docker run itd --volume. The volume of, I want to load it at the folder home/mount/volume1 at the location /app and using the image nginx. Okay, so now we will do the ps command. And these are listing the containers. Now let's exec into the container. So docker exec it and the container ID and bash. Now let's cd to the /app folder and then list the files here. You see the file test1.txt is here. So now let's check the content. The content is also present here. Okay, so now let's add some text into this file and then we will append it to the test1.txt. Okay. And also now let's exit from the container. Now if I do the cat from the docker host cat test1.txt, we will see that the file was updated from the container. Now let's run docker volume ls. As expected, we don't see anything out here because the current volume is done using the bind mount and it is not the volume. The second exercise is to launch a container with bind mount using the --mount flag. So let's do that. On the Docker host, I have a directory called /home/mount/volume2. If I check in this, there are no files in this directory. Now we will create a container and run this command here. Okay, so I'll create this docker run itd mount. Type is bind and source is this particular folder path. And I want to bind the file inside this directory. Let's say config.txt. And the target inside the container is /app/config.cfg. And of course, I want to use the nginx image. As the source file didn't exist as we expected, let me add some content to this config.txt. So echo added some content and then let's put it in config.txt. Now let's rerun the command docker run which we previously ran. Now the container started successfully. If we do docker ps, it will start showing the container. Let's exec into this container -it and the container ID using bash. And now let's cat this config.cfg file. So the file is now available inside the container. The last way to mount the volume is tempfs mounts. As opposed to the volumes and bind mounts, a tempfs mount is temporary and only persists in the host memory. When the container stops, the tempfs mount is removed and the files written there won't be persisted. Tempfs mount is not persisted on disk, neither on the Docker host nor within the container. It can be used by container during the lifetime of the container to store non-persistent state or sensitive information. When the container stops, the tempfs mount is removed. If a container is committed, the tempfs mount is not saved. Best use case for this one is when you do not want the data to persist neither on the host machine or within the container. An example might be a temporary one-time password that the container application creates and uses as needed. Unlike volumes and bind mounts, tempfs mounts cannot be shared between the containers. It is available only with the Docker on Linux. For tempfs mounts, you can use the tempfs flag or the mount flag. The only difference is that the tempfs flag cannot be used with the services in the Swarm cluster. Okay, so for this first exercise for this is launch a container with tempfs mount using the tempfs flag. So let's get back to our host and run a container there. So docker run itd tempfs and the mount point is at amp and the Tomcat image. Now let's see the status of the containers. We can see that the Tomcat container is running. Let's exec inside this container with this container ID and bash. Let's go to the directory /app. Let's try listing the files inside. Now currently there is no file. So let's create a file, echo some text to the mount point and then give it to the test.txt. Now let's exit and let's have a look at this. Now text.txt is created. Now let's exit out of this container. Now we will restart this container. We know that in case of tempfs mount, the data doesn't persist, right? So let's do a docker start and this container ID. Okay, this started, right? So we see that there are three up. It is up for 3 seconds and has been created quite some time back. Now let's exit into this container. The container ID and the bash. Let's go to the /app folder and list the contents. As expected, there is no file. Now let's second exercise, launch container with tempfs mount using the mount flag. So let's go back to our host and run a container. Okay, run itd mount. Type would be tempfs and this time we will give destination instead of source. So the destination would be our /app folder and the image would be Tomcat. Now let's go back and do the PS. We see our container is running. So docker exec it and the container ID and bash. Now we are in the container. Let's go back to the app folder and ls there. There is no file here. So this way we understand that the tempfs mount is temporary and the data persists only in the host memory. Hello everyone. In this nugget, let's discuss the external storage for the Dockers. We have seen earlier that Docker uses volumes only to store data on external systems. Docker provides volume plugins which can be used for persistent data storage external to the host. In case of external volumes, even if the Docker host goes down, the data isn't lost. The external systems have their own mechanism which Docker need not know about. So while creating the volume, we can specify the driver to be used. Now, a list of such drivers can be found on this particular link. So let's get back to the browser, and here on this I have already opened that link. It has the complete list of supported volume plugins. Here you can get it. So we can also create our own drivers instead of being relied upon the existing drivers that the Docker provides.